William John Banks, who was one of the most sort of sparkly of the Banks family who lived here at Kingston-Nacy, at the beginning of the 19th century went to one of the most remote parts of the world because he was fascinated by Egyptian architecture and culture. He went up the River Nile with a couple of his friends right up to the Second Cataract, went to a beautiful island called Philae, and landed and went up to the Temple of Isis. And in front of the Temple of Isis he saw this obelisk lying in the sand. And being an inquiring sort of man, he looked at it and saw that there were two inscriptions, one in Greek and one in hieroglyphs. And because he could read Greek, he understood what the things said, but then made a link between some of the words that he saw in the Greek inscription and the hieroglyphs. And in so doing, he sparked an idea that was ultimately to lead to the decipherment of hieroglyphs and 4,000 years of Egyptian history being readable from monumental inscriptions. Now, the link with the space mission is of course this, that the European Space Agency have sent out this lander, which is called the Philae lander. 800 million miles away now, it's going to land very soon. But what they hope to get from analysing the comet is trying to determine really the origins of our planet. And they think that that will do for space research what the understanding of hieroglyphs through the Philae obelisk did for the understanding of ancient Egyptian history.
What we do with Rosetta, we look back, so to say, in the infancy of the solar system. So we do archaeology as well in space, but on much longer time scale. So we look back 4.6 billion years at the time when out of the pre-solar nebulas the planets formed. The landing on a comet will be the first in history of planetary science. It's very difficult because comets are low density objects, very low gravity, and comets are changing all the time because they produce, so to say, matter. They outgas when they are heated up by the sun, and that will disturb the lander. So it's very complicated. First of all, we have to be at the right time, at the right spot to release the lander, and the lander will go down passively, which is also first because we couldn't put a huge spacecraft to carry there, and therefore there are a lot of challenges. Secondly, we don't know what the surface is that the lander will land on, because we only will learn with the lander. Yeah? So these were things that made it very complicated. We had to, so to say, design into the unknown when we designed the lander, or our colleagues, about 15 years ago. We didn't know anything about this comet, and now we are there. We know it's very irregular shaped. The surface is very structured, so it's a challenge. The irregular shape influenced the selection of the landing site, because it's very difficult to find the right spot, because the lander has to see sunlight most of the time, not always, and it's also to find, because the irregular gravitational field, you have to find the right spot where you can put it down. Therefore, we have to release the lander at a fairly high distance from the surface of the nucleus, and it takes about 7 hours to come down. And then we have to have basically luck where we get down, because the landing ellipse, that means the area where the lander could come down, it's not a point landing, it's 500 meters. And in this area, if you look at the nucleus, there are still craters and cliffs, and a little bit of luck we need that the lander is not falling off a cliff and that it comes down on the 3 legs. The signal at that time, because we are far away from the Earth and far away from the Sun, takes about 28 minutes and 20 seconds. So as after the touchdown, at least it takes this time till we know if it worked. But we will follow it up during the descent.
I was involved in the design of the Ptolemy instrument, which is right in the heart of the lander behind us there. It's a gas chromatography mass spectrometry instrument, and it can measure the isotope ratios of the chemical species present in the comet. There's an awful lot of work in general for the space instrumentation, is that you're trying to design things that are very reliable, will survive the launch environment to start with. You've got a very rough ride on top of the rocket. So the first thing we look at from an engineering perspective is making sure that it'll survive the vibrations of launch. You've got to design an instrument which is very lightweight, because ultimately the payload has got a maximum mass that the launch vehicle can put into orbit. Then there's the thermal environment, so we obviously started off on the Earth, but we circle the Sun several times and end up going out into the solar system as far as Jupiter. So you're going from the warm-ish environment around the Sun right out to the orbit of Jupiter. It's a very cold environment, so there's a lot of thermal engineering goes on to make sure that the instruments can survive the challenges of different temperatures that it'll see as it's orbiting around the solar system. One of the main concerns on this and other instruments is also the accommodation. You really don't have a great deal of space. Everyone's fighting for real estate to get their science on board the lander. So yes, there was an awful lot of head scratching as to how we were going to fit this room full of scientific equipment at the Open University down into a package the size of roughly about the size of a shoebox, along with the electronics and the computing that needed to drive it, and then package it into the middle of the Rosetta lander, which is surrounded by lots of other instruments as well.